Hi there and happy Christmas. Now, at this point in your programming career, and I'm going to assume that you're going to have a programming career, it makes sense for us to start breaking up our program into multiple files. Because as soon as you start writing bigger programs, you're naturally going to want to compartmentalize or modularize certain aspects of it. So say you've got a whole bunch of files that perform numerical operations, you might want to put them in a separate file called numerical operations.c. Now, in order to do that, or as a correlate of that, we're going to need a way to compile our program with multiple inputs now, if there's multiple files that our main output program depends on. And in order to do that, we need some kind of build script or build process. You can manually do that, but nobody does. It would be a complete hassle for a very complicated program. So what we use is something called make. Well, that's one way to do it, and it's a very common thing that you see everywhere, so it's definitely worth covering. Now we're going to look at GNU Make. There's several implementations. We're going to look at the syntax of GNU Make. The syntaxes of the other implementations are very similar, but GNU Make is probably the most common. And what make allows you to do is when you have a program with lots of complicated dependencies, like files, so your main program has lots of dependent files, each of those in turn depends on other files, it allows you to recompile your complete program and only recompile those dependencies which have changed. In order to do that, make allows us to specify a target, a bunch of prerequisites. I'm just going to write that's pre-R. We then have a tab, and we have a rule. And to build our target will be updated if it doesn't exist, or if any of the prerequisites have changed. And in order to build our target, we follow the rule. That probably seems a little bit obscure, but don't worry. We're going to go right back to what we already know. So far we've been compiling a single file, and have some sympathy for the people, the early pioneers of programming, because they often always wrote the entire program in a single file. And sometimes they had to feed that entire program into a computer kind of byte by byte, probably in machine code, using either a punched tape or perhaps even manual switches. Whereas these days we've got a lot more flexibility in writing programs. Now, so what we've seen so far is we've got a single file, something like hello.c that perhaps just prints out hello world. And what we've always done is we had a Makefile. So we had a file called Makefile. So we've already been using make. And inside that file, we saw the following. We had a target, so I'm using the terminology we've just seen, and our target was called default. So make, when you invoke make on a Makefile, it always executes the first target it finds. That's what it does. But it only does that if the if either the target, if this is a name of a file, then if that file already exists, it won't execute the target unless the prerequisites have changed. But all we had was a single target and the name hello. So what exactly was going on here? Well, actually, the target default had a prerequisite called hello, and we did not specify a rule for it. So what this means is that because hello is a prerequisite, it will then will look for a target called hello and try and build that, because it knows it needs to build hello in order to build default, which is what we're trying to build. But there is no target in our Makefile for hello. We could write one. So let's write one just to see that we'll get the identical behavior. In order to write a target for hello, we write the name of the target, then we write the prerequisites. And the prerequisites for our hello executable are hello.c. That's just a single file that we use to compile it. And then the rule for building the target hello, this is a tab by the way, and it's immediately on the next line. So Sorry, excuse me, someone's calling me. That was my wife, she's on her lunch break. Right, so where were we? So, default's our target, and the prerequisite for default is hello. So we're creating a target for hello. The prerequisite for hello is hello.c, and the rule for building hello is the following. By the way, C compiler, is almost always aliased to the default compiler on your system, like GCC or Clang. So you'll actually usually see this outputted on the command line rather than Clang or GCC. Now, we're obviously taking our file hello.c and we produce an output file called hello. And that is actually it. So when we call default, it goes to target hello. There are two ways in which a target can trigger a rule to be built. First of all, if this is a file name, so if the target is a file name and it doesn't exist and there are no prerequisites, then the target will be built. The target will be built, actually regardless of the prerequisites, if the file doesn't exist, because we need to build that target. The other circumstance which can trigger the rule to be executed is if the file, or any of the files in the prerequisite list, or any of the targets, because you'll see that we can actually essentially nest targets. So if any of the prerequisites have changed, then the target will be rebuilt. Changed? Changed since when, you might be thinking? Well, changed since we last called make. So whenever we call make will keep track of all the prerequisites and all the files in those prerequisite lists, and it will remember, it will take a hash of the file, and it will know when that file has changed. It probably just looks at the date of the file or something like that, the modified date. But, yeah. So if the file has changed, then it knows that the target needs to be rebuilt. And that's the kind of behavior that we want, because whenever we change a file, then we want the target to be rebuilt. Now, so that's actually what's going on with our default case. Although we've explicitly put the rule in, there's an implicit rule that make knows how to compile a file when there exists the same name with a .c extension. So when your target is a file, or is a name, and in that directory there exists a file with a .c extension, it knows to do that. That's why we don't have to provide this target explicitly, and that's called an implicit target. There is another implicit target in Make called which builds object files. So say we had and we're going to look at this in a second. If hello depended on an object file called func.o, which might contain contains a bunch of functions that hello needs, then our compilation step would also include func.o. It's called an object file. Just imagine this is on the same line, and then it would still have our output specification. Now we have a separate object file, so we need to create a target for it. So we'll look for a target to build that prerequisite. And so func.o will depend on, its prerequisite will be func.c. There's a tab here. And then what we do is cc, and we use -c to create an object file, func.c. And so that would be the rule to build an object file. And this is another implicit rule. Whenever you have an extension .o, if in the same directory there exists a file with a .c, then compile that file but use the -c flag to create an object file, which can then be used and combined in another compilation step to produce another program. We're going to look at this just in a second, but what we've also seen here then is that we have a target hello, which has a prerequisite, which is another target. And that target is an object file. And what you can see is that if, say, func.c changed, that means that this target would be out of date and would be rebuilt, which would trigger this target to be rebuilt as well, because this prerequisite will be out of date. So in that way, changes cascade kind of upwards from the lowest dependents and trigger recompilation changes. And that's very useful. But also parts that haven't changed, parts in the kind of tree of compilation, do not get recompiled. All right, let's take a look at that stuff so that we understand it more. So what we've got on the left is a file called hello.c, and in our Makefile we've got the thing that we've done so far every time. We have a single default called hello, and when we type make, you can see that it invokes cc with the file and then specifies an output file, hello. So let's create an explicit target. So we can say that hello is a target that depends on hello.c and then we'll actually explicitly write. Now if we compile that, okay, there's nothing to be done because we haven't changed the file. So let me just remove the object file, and there you can see. So this time we're compiling it using our target, and you can tell that it's our target because the spacing is different. Like the spacing respects exactly what we have put in our spacing. In Makefiles you can put comments, by the way, which you precede with a hash. So this is a comment. Now let's have a look at those default targets that I was talking about. So I said if you have a target that is the name of a file, and if a file exists in that directory that is the same name as that target, that ends in .c, then there will be an implicit target executed, implicit rule, executed for that target. So what we've got is a name here, and we've literally just got the target, and there's no prerequisites. So let's see what happens. Okay, again, let me just remove the old one. And you can actually see then that implicit rule has been executed, so we don't have to specify it. And let me show you the rule then for the object file. So we'll create another file called test.c, or no, let's call it func.c, and we'll just add in there a function, hello func. And all this is going to do, it's going to be a void function, it's going to print hello there. Now, in our Makefile, we could have a target called func.o, and we're not going to put any rule or any prerequisites. Now, ignoring the warning, because yeah, we haven't included printf, we should include print standard.io.h. We should include standard.io.h, but we didn't. So ignoring that, just look at the rule that was actually executed. So we used a -c there, specified the object file, and the input was func.c. And of course we can do this manually ourselves. So by the way, the output file will, if I remove func.o, just to show you this, and if I compile func.c with this -c tag, you'll notice that func.o has been generated. So the default output name would be func, or the target file with the .o appended, but we can also explicitly say func.o. In fact, let's do something different. Funky.o, and then you can see that there's a funky.o. So that's two implicit targets, one for object files and one for executable files. And all of our C programs are going to be comprised of C files, header files, which are never compiled, object files with .o extension, and library files, static libraries and dynamic libraries. And they're the only things we will ever pass into our executable, our invocation of the compiler. Now, let's now then actually write a more complicated target. So we will get rid of some of this stuff. And I'll tell you what, in order to get rid of it, we'll add a new target into our Makefile. We can have a target called clean, and since it's not the first target, it won't automatically be executed. And on the next line, we put a tab, and then we can actually say rm star.o. So we'll get rid of all the object files if we run make clean. We can then execute that target by typing make clean, which removes all the object files. And we might want to remove hello as well if we're cleaning. So we can remove hello as well. Sorry, I just typed make, which does the default one. Make clean. There we go. Now, so let's create something sensible. In our func.c, what we're going to do is create what's called a header file. So here we're now looking at the intersection between Makefiles and spreading our program out. Remember, whenever we want to use something like printf, we need to include standard.io.h. Well, we're going to use our function hello_func in our program. So we need to create a header file for hello func so that we can declare that function before we use it. So this is going to include func.h. So where our function is defined, it's going to include func.h. Then in func.h, we then define our function, or sorry, we declare our function. And our function was a void function called hello func, and it took no arguments. And what we will also do here is include standard.io.h, since that is required by our func.c program, because we're using printf. So now we have func.c and func.h. In our hello.c, we will now include func.h, and because we've included it, it knows about that function now, and we can call hello func. But we need to edit the Makefile here. Now, there's a couple of different ways we can do this. So we can say that our program hello depends on hello.c and depends on func.o. And because we have an implicit rule for func.o and there's an implicit rule for .c files, then that should be enough actually to build the program. And what you can see has happened here when I've typed make is the first thing that happens is we use a .c flag to cc to compile this object file func.o from func.c, and then cc is invoked with hello.c and the object file to produce our output file hello. And if we now invoke hello, we can see that we print out this is a test program and we print out the function that we called. If we did not include func.h, so if I just comment that out, then we get implicit declaration of function. So the function, we didn't know what the function was. Same as if we didn't include standard.io.h. So that's what header files are for. And header files include just the declarations of all of the functions that are defined in the corresponding C file. So that's just the function with any parameters but with no body, so there's no bracket after it. Whereas in the actual place where the function is defined, we've obviously got the body. Does that make sense? So when we compile func.c, we get this func.o, which then essentially just contains this function, which we can then use in our hello.c main function, main program, and call. And the only distinction in those two calls is -c is used to compile an object file. We can then, just to finish this off, we could explicitly have targets here. So we could say that hello depends on hello.c and func.o, and we could say that the target for hello, let's actually use clang directly, is to compile hello.c along with func.o and create an output called our program. And then we'll have a separate target for func.o. So we'll create an explicit target even though an implicit one already exists. And we will say that we're going to call clang on func.o, and we need to use the -c. I'm going to create a, sorry, on func.c, I'm going to create an output called func.o. So let's have a look what happens when we call make. Well, since func.o already existed, we didn't call this target. So let us actually either modify func.c or remove func.c. In fact, what we would want to do, just to be clear, func.o depends on func.c and func.h. So by saying that, we're saying that if any of these two files change, then we're going to recompile func.o. We're going to recompile this target. So if I now go and change func.h, and I'll just add a comment in here, anything we do to change that file will cause it to be rebuilt. Now you can see what's happened is func.c has been rebuilt because of that, and we've invoked the rebuilding of our target hello, and we've produced an output called our program. Our program exists and it prints out the same thing as before. I know there's quite a lot to take in there, but hopefully you can kind of understand what's going on here. So this is a target, these are its prerequisites. Each of its prerequisites are checked in turn. So if we didn't have an explicit rule here, there would be an implicit rule to build hello.c. But there is an explicit rule, so this is what's going to be executed. This target is checked, func.o, we go down here, we check its prerequisites. If any of these files are changed, we execute this. Also, because it's a .o file, there is an implicit target for it, so we don't actually have to specify this, but there is a reason why we might want to specify this. You can imagine that you might be building a particular object file and you might want to turn optimization on or off for that particular file, or have some particular way that you want to compile it, you know, some special thing that you want to do, where you want to do that. So that's the very first basic introduction to Makefiles. So it looks like we're actually going to talk quite a lot about splitting up files, and it's complementary to talking about Makefiles, it seems. So you can split your program up into as many files as you want, and you can separate it out chronologically. You will always need, if you want to create an executable program, one of your files will have to have, one and only one of your files will have to have the main function, because that's the function which is executed when your executable program is ran. The rest of the files will not have a main function, but they will have other function definitions. So if you want to put all your numerical functions into a file, then these, let's just call it numph for brevity. You will have a file called numph.c, which will contain all of those functions. It will contain the definitions of those functions. That is everything required about those functions to run them, the body, all of the code for them. And you'll have a file called, if I can write, called numph.h, which is the header file for the C file, which will contain all of the declarations. Then you will, when you have your main.c, or whatever C file contains your main function, you can then include this header file and include the declarations of those functions that are defined in numph.c and use them. And then what happens once you use them, you compile main.c along with your object file that's created when you compile numph.c, which gives you your numph.o, and then you produce your output. And you can put as many object files as you want. You can link against as many object files as you want. So these are called include files, the headers. So they're included and they provide definitions for functions. These are called object files. In a way, you can think of these as a little library. Like when you compile numph.c, all of those functions are essentially available in this static library. Well, that's a special kind of library called an object file. But when we link against external libraries in the next episode, you'll see that they're actually reasonably similar. And also creating our own libraries will be a process of bundling up a whole bunch of object files into another type of file that we can then link against. The compilation step, the reason this is called linking is because in this step actually we're compiling main.c and linking, but traditionally that was separated out into two steps and it will be performed as two steps by the compiler. We compile main.c and then we're linking this object file with this function to get the end program. And it's called linking because we're kind of linking together all the disparate elements of our program. Like some of the functions are over in this bit, some of the functions are in some other object file, and we're linking them all together. So we can actually have as many object files as we want. In fact, we can imagine a scenario where we've got tons of different object files because we've split our program up into lots of different parts. Like it might not just be function, like a particular set of functions in like numerical functions in an object file. You might have a separate C file for different kind of hierarchical or structural parts of your program that make kind of semantic sense. So imagine if we were trying to represent a car, for example, just to give a crude example, we might have a function called engine, not a function, a file called engine.c which contains all of the functions to do with that, and suspension.c and chassis.c and so on, and then we might have some other files that tie that together. You see what I'm saying? Like you might want to break it up like that. And once you start writing programs, the program will start getting too big and you'll kind of feel like, I need to break this up, I need to make this more easy to manage, like easier to reason about, and you'll sort of naturally know how to do it. So imagine that we compiled these as A.O, B.O, and C.O, and then we had some car.c which contained our main function. Then we might compile this with cc car.c A.O, B.O, C.O, output car. So all of our object files will be passed into the compilation command to produce our output. So it's quite simple. For each file that you want to put functions in, put the functions in there, put their declarations in a header file, and then link them all at the end to the function, the program in which you're using those functions. Of course, in car.c we're going to include the header files for each of these. So we'll probably include engine.h, suspension.h, or chassis.h, whatever header files we need to include for the files that for the functions we're trying to use. Hopefully that makes sense. Okay. So, going back to Makefiles, when we have a lot of object files like this, it can start becoming annoying to have to keep writing them out, like to have to write out A.O, B.O, C.O, especially if we actually use the longer names like engine.o, suspension.o that were created. So luckily Makefiles support variables, so we can say like variable equals A.O, B.O, C.O. And then we can say cc, in our target rule, we might say cc car.c $ bracket variable o car. So we can reference variables like that, and of course the variable has to be defined before we can use it in our Makefile. So in order to explore the idea of having multiple files, what we're going to do is we'll create a file called a.c, and this is going to include a file called a.h, and it's going to contain a single function which is actually just going to be called a, and it's going to print out I am a, and of course we need an a.h, and in fact a.h is going to include our standard o.h rather than a.c. And we just need to write the declaration for this function, so it's called a and it returned nothing. I want to increase the number of files that we've got, so let's copy a.c to b.c, let's copy a.c to c.c and d.c, let's copy a.h to b.h, to c.h and to d.h. Now if we list .c files, you can see we've got A, B and C and D, and we'll create a file called multi.c, and in this one we're going to include standard io.h. We don't necessarily have to, because our other include files are going to include it themselves. But the thing with including files is, for things like standard io.h, they will only be included once. There are ways to make your file be only included once as well, which is a problem that you will encounter once you start working with lots of files. So we're going to include all 4 of our header files. We're going to have a main function that is just going to call each of the functions and then return. So if I open b.c, we'll make this so it's prints out I am b. We obviously need to modify b.h so that it only contains that function declaration. Now if we open c.c, it's going to include c.h, and it's going to say I am c. And then we obviously need c.h, contains the definition for the function c that we've defined in c.c. In d.c, we're going to have the function d, and it's going to say I am d, and include d.h. And then in d.h, we need to have the declaration for our function d. So that's all the files, and now we need our Makefile. Now because we've already got a Makefile for some of the other examples, what we can do, make allows you to use a -f to specify the Makefile. It's quite rare that you would use that. Usually you have a single Makefile in a given directory. But because we can use that, we can then create a file called Makefile multi. And what we will do is we're going to have our target for multi, and we know that there's already implicit rules, so we can just say it depends on a.o, b.o, c.o, d.o. And what we'll do is, because we don't want to type those out again, we're going to use a variable, and so we're going to say that the objects are these. And so multi depends on multi.c and the object, so we're using a variable, and the target for it is going to be clang or cc or gcc, whatever you want. And we're not going to use any automatic variables because we can automatically refer to all of these using a special variable. We're not going to do that for now, so we're going to still write multi.c, but we're not going to write all the objects out again. We're just going to do that. and the output program is going to be called multiprog. So if we're going to call our output program multiprog, so that make works properly, we should actually make our target multiprog, because it will actually look for that target, look for that existence of that file. So there we go. And we don't need to bother with targets for these because we know that they'll implicitly be built. So let's see what happens when we invoke this Makefile multi. And you can see that all the dependencies have been created first. All these 4 object files, and then of course we're invoking Clang then with our multi.c, our 4 object files, and producing our program. If we now run the program, we print out the 4 functions. Our 4 functions were distributed over 4 different files, and as you can see, it's pretty straightforward. The last thing that I want to talk about is what's called automatic variables. So here we have an explicit variable, so it's a non-automatic variable, if you will. Now what you'll notice is that, the variable is allowing us to then substitute it here and here, so we don't have to write these object files out again and again. But what you'll notice is that we're writing out multi.c twice, and that our output name is quite often the same name as the target. So the automatic variables allow you to reference things like the target name, and it allows you to reference the prerequisite list. So we can actually rewrite this like this. Target's the same, obviously. And this is all going to be the same. You can't use automatic variables in the prerequisites. We've still got our tab, of course, and CC, but instead of writing that out again, we use $, and then a caret, and that means all of the prerequisites separated by spaces. And then for our output, what we can use is another one, $@, which means the target name. So this can become very useful when you've got lots of object files and so on, just to shorten what the rules look like. And you can also use make in a more advanced way to define generic rules. So like you can say if I'm operating on an archive file, unzip this thing or whatever, you can define generic rules based on file extension and so on. And then these come in quite handy because you essentially need that to define a generic rule, because you don't know what the name of the objects are going to be. So what we're going to do is, to show the automatic variables, we're also going to do a nested or kind of hierarchical makefile at the same time. So we need to create a new makefile. I'm just going to get rid of this, I've just been practicing around. So we need a new makefile called Makefile nested, which we'll keep over here. And over here we're going to create a new file called bnested.c. And in bnested.c we're going to include our bnested.h. We also need standard.io.h. And we are going to have this function called bnested. And bnested is going to call B, C, and D. So for it to call B, C, and D, it will need B.h, C.h, and D.h. Otherwise it won't know what those functions are called. Then in bnested.h, we're just going to have our function defined. Right, now we're going to create a program called, just call it nested, why not? And we need standard.io.h, we need our bnested.h, and we need a.h. Our main function is going to call a, and then it's going to be called bNested, which we know in turn is going to call B, C, and D. So on a Makefile, we'll have our target for nested, and it's going to depend on a bunch of objects. And what you'll notice here is actually this is going to depend on all of the objects, because that's where the functions are. We need to include all of the objects which the functions are in. So nested, bNested.o, when it's compiled, although it uses A, B, and C, B, C, and D, it doesn't define them. So we still need to include these objects to link against nested.c. And bNested.o. And so they're actually all our objects. So I'll tell you what, we'll put those in a variable. And we'll say this obviously depends on nested.c, and it depends on the objects. And then the target we'll call clang. And we're going to use our automatic variable here then to say all of the prerequisites. And then our output is going to be this name here to compile it. Now, since these are all object files, they will actually all be compiled implicitly. And let's test that out. If I call make with the nested Makefile, we actually see here is then that these were all compiled. So even bNested.o was created from bNested.c, and there was no complaints about the not being able to see these functions, because all we needed to see was the declarations of those functions when compiling bNested.o. So we're not linking against that object. That object will have unresolved symbols in it. What that means is the functions that we called, B, C, and D, at this point are unresolved. They all get resolved and linked together in our final linking step, compilation and linking step, where in nested.c, when we call bNested, in bNested.o, we will realize that we're calling B, C, and D, and then we'll search for all of the objects that are passed to clang, and it will find them in here, those functions, so it will resolve them.
Okay, so that wasn't actually really a hierarchical makefile. There was only one line in the end. Never mind. It's not difficult to do a hierarchical one, and so we've just seen the automatic variables. So the last thing that I want to look at is if you want to create your own pattern rules to do sort of custom actions on files. And to do that, I'll just illustrate, for example, what the pattern rule for compiling a C file is. So we use a %, and this is going to match the files in the directory. So actually everything to the left of this colon, because this is a target, is going to match files in the directory. So this is the pattern matching rule for the implicit rule for compiling C files, and it says, so this one's quite straightforward, and it will look for this stem. It will try and match a file. In fact, now of course, if you think about what's happening here, we always need something like an actual target. So if we had a default target called hello, it will look then for a file called hello, because this is going to be replaced by the target. If it can't find a file called hello, it looks through the prerequisites. So it looks for a file called hello.c. If it can find hello.c, then it executes the target, and it will compile essentially the target hello, because this is our output using the automatic variable %at. and the input to CC is going to be all of the prerequisites. I think in this case there's only one, and that will actually then produce the target. And by the way, you look up if you look up online, you'll be able to find all the automatic variables. You can also, so let's look at the one for the .o files. It's quite similar. So we're just using cc-c, all of the C files, and then the output file is going to be the target again. So how this one will work, I mean, imagine in our target if we had a.o as a target, or as a dependency of some other target, then it will look here and this will match, a.o will match, and this stem will be substituted for a, and then we'll look for a.c in the local directory. If that exists, we know we can build this, and that will produce a.o. So that's how that's two examples of rules, pattern rules, and that is the implicit pattern rules that actually exist and allow the implicit building of C files and object targets. Let's create another one, and in my directory on the computer I have a file, text file, let's call that x.text, and what we want to do, we want to create another file called x.text.end, which is just the last 10 lines of the file. So what we do is we say, so stem.text.end, and it's going to be stem.text, then we need our tab, and what we're going to do is we're going to cat the input. We're going to pipe it into tail, and we're going to do an end, take 10 lines, and then we're just going to redirect this is all on one line, into the target. So we're just taking the last 10 lines of the file. And so what this will do is when we try to build x.text.end, it will look for it, it will match this rule, x will be substituted for the %sign, and then we'll look in the directory for x.text, i.e. the input. If the input exists, then we perform this rule which will produce the output. So that's how you can use custom rules to perform custom actions on targets, arbitrary targets and arbitrary things you want to build. So we're going to look at custom patterns. First of all, I need a file, a text file to modify. And we're just going to take the last 10 lines of it. So let's put something in here that we can easily examine. There we go, it's got the alphabet in it. And so what we're going to do is we're going to have a single default target, and the target is going to build x.text.end. And the pattern for this is going to look for a stem called x.text.end, so it's going to look for a file that matches that pattern, and if that doesn't exist, it's going to look for the prerequisites, and it's going to look for a stem x.text. If it finds anything, sorry, not x.text, pattern.text. If it finds anything that matches that, which will of course match x.text, it will then build our output, and our output is going to cat the input, pipe it through tail, take the last 10 lines, and then output it to the target. Okay, that's it. So now if we call make with this new Makefile custom, you can see that what it's done has created
our target file, and if we cat x.text.end, we see that it's taken the last 10 lines. So it worked as we expected. So what's worth mentioning here, because we were looking for that target and this pattern matched, we then determined what prerequisite was going to look for, because this matched an x, so then we looked for the file x.text.
Okay, that's all I want to say about Makefiles. This is a sort of basic introduction. Next time we're going to look at libraries, external libraries, and creating our own libraries. And I think and that will also help. We'll be looking at Makefiles again then. Alright, well, thank you for watching, and I'll see you next time.